In this lesson, we're going to discuss acid-base titrations, and this is a very nice application of all the work that we've been doing to calculate pH of various solutions. We've calculated pH of strong acid, strong base solutions. We've calculated pH of weak acid, weak base solutions, buffers, and of solutions after some concentration of strong or acid or base has been added. Now you'll recall from your studies in grade 11 that a titration is a lab procedure where we are analyzing an unknown solution. We refer to this as a volumetric analysis because we are adding a certain volume of known solution to a certain volume of unknown solution. And the goal is to determine the concentration of an unknown solution. Now what's important to note is that titrations don't always have to be acid-base titrations. We're going to see later on in the year that we can do redox titrations, we can do precipitation titrations. So it's important to think of this as a volumetric analysis procedure rather than something that we use to analyze acids and bases. The burette, you'll recall, is the glassware that we use to add controlled volumes of the standard solution or the titrant into our unknown solution. So the standard solution is the one that is of known concentration, and you learned in grade 11 that there is something that we refer to as a primary standard, and the classic primary standard in acid-base chemistry is potassium hydrogen phthalate. So it's important that you understand that a primary standard is one where we can basically be really confident in its concentration. You'll recall that sodium hydroxide is deliquescent, or it absorbs water, so it's really difficult to prepare a solution of known concentration of sodium hydroxide, although it's a very useful titrant or a solution that we put in the burette in order to study acids and bases. The acid-base indicator is the substance that we put in order to help us to identify the end point. We're going to discuss indicators in a little bit of detail later on in the lesson. As you know, the classic acid-base indicator that you've used so far is phenolphthalein. It's colorless in acid and it's pink or magenta in base. Now the end point of the titration is the point where we stop titrating, so we no longer add any of the titrant from the burette, and this occurs when we observe a color change. Now the goal of completing a titration is actually to determine the equivalence point. We're trying to find the point where the two reactants are stoichiometrically equal. So the moles of acid, for example, is equal to the moles of base, or H plus and OH minus. That is the equivalence point. Now we want to choose an indicator that's going to change color as close as possible to the end point, because that's what we're using to identify the equivalence point. We're going to examine three different types of acid-base titrations. We're going to look at the titration of a strong acid by a strong base. We'll look at the titration of a weak acid by a strong base, and we'll look at the titration of a weak base by a strong acid. Last year, the focus was, when you created titration curves, the focus was a strong acid and strong base. And you're going to see from your advanced knowledge of acid-base chemistry that these ones, the last two, have a bit of a difference. And you're going to notice that we don't do a titration with a weak base and a weak acid. The systems are far too complex, and so they're not ideal. So this should be familiar to you. This is the picture of the titration curve for a strong acid with a strong base. Okay, a few features of the curve. We can tell by looking at the pH that we're starting with an acid, so in this case the titrant, or the solution in the burette, is the base. So we are adding base in increments, and we're measuring the pH at each of those increments and graphing the results. Now when you have a titration curve, there is always a very steep part of the titration curve, and that always occurs around the equivalence point. the point where the moles of acid is equal to the moles of base. In this case, we're titrating a 0.1 molar hydrochloric acid solution with a 0.1 molar sodium hydroxide solution. We're starting with 25 milliliters of the acid, and so the equivalence point here occurs at 25 milliliters of base, and the pH of this solution is going to be 7. The reason it's 7 is because the products here are water and salt, NaCl. And as you know from your study of salts, that if a salt is produced from a strong acid and strong base, like NaCl is, it will not affect the pH, and therefore the pH is 7. This point of the curve, the equivalence point, is actually an inflection point. So it's the point where the curve changes from being a curve that's increasing to a curve that is decreasing. And when we're studying these graphs, in order to find the equivalence point, we actually need to take the halfway point of the steep point of the curve. Okay, so we look at the steep part of the curve, and the halfway point is where the equivalence point is, which in this case is pH of 7. Now what we're going to do is look at how we can put everything together that we've used already to determine the pH, calculate it at different points throughout the titration. So let's look at the pH before the titration begins. We started with a solution that is 25 milliliters in 0.1 molar hydrochloric acid. Hydrochloric acid is the only solution present, and it's a strong acid. So we know from this that the concentration of the H plus is going to be equal to the concentration of the HCl. So for this particular solution, the pH is simply the negative log of the concentration of the H plus, which is 0.1. Okay, so initially, the pH of the solution is 1, which, if we look at the table associated with the curve, it matches. Now, let's look at the concentration of the H plus and subsequently the pH after a certain amount of base has been added. We're talking about the region before the equivalence point here. Okay, so we're dealing with a strong acid and base, and if we're before the equivalence point, we have a scenario where we have a limiting reactant. So what we need to do is look at the reaction that we have. And remember, anytime you have a reaction with a strong acid or a strong base, so in this case we've got both, it's going to be a complete reaction. So we're going to have a full arrow here. In order to organize the data to see what we have left over, we're going to set up an ICF chart. Now, what we have is we've got a volume of 35 milliliters for the total, because remember, we started with 25 milliliters of the acid, and we've added 10 milliliters of the base. So a very, very important initial step in all of the calculations that you're going to do in this section will involve you diluting the given solutions. Because during a titration, we're not adding solid quantities, we're adding volumes of solution. So if you do the C1V1 equals C2V2 with the given 10 milliliter and 25 milliliter solutions, what you see is that you get a concentration of sodium hydroxide, which is 0.285, and a concentration of HCl, which is 0.0714. Now in this case, you can see that the sodium hydroxide is limiting, which makes sense because we're before the equivalence point, and so the limiting reactant is going to be completely consumed. HCl is in a 1-to-1 ratio with the NaOH, so the concentration of the HCl that's left over here is 0.0428. Now when we are dealing with buffers, we would have needed to look at this side of the solution and look at the ions that are put into the solution. But because sodium chloride does not affect the pH and H2O is a pure liquid, it doesn't affect our calculations, there's no need for us to look at how much NaCl is in the solution. Now, if we look at this, what we have left over in the solution at this point is strong acid. This is where the key decision making comes in. You always need to be conscious that you're making a decision that you've got a strong acid. The strong acid will dissociate completely, so that will put into our solution a concentration of H plus at 0.0428. Okay? And as expected, it's decreased. Originally it was 0.1, so it's decreased a little bit. So the pH here is 1.36. Okay, so far the pH has risen from 1 to 1.36. And it's not too large of an increase. The beginning part of a titration, the pH changes gradually. And let's look at just before the equivalence point. So when we've added 24.90 milliliters of the sodium hydroxide solution, which if you look at the beginning, it's 0.1 in its concentration. Okay, so right now our total volume is 49.90. So again, we've got the reaction of NaOH with HCl. Okay, I'm going to do my ICF chart. The concentration of sodium hydroxide in this solution is 0.0499. And the concentration of HCl is 0.0501. Okay. And so the sodium hydroxide, again, is our limiting reactant, so it's going to go to 0. And the concentration of HCl that I'm left with is 2 times 10 to the negative 4. And so the pH still hasn't risen too much, but it is making its way upwards. And the pH at that point is 3.9. Oh, sorry, it's 3.7. Just put it over. Okay, so it's 3.7. Now, if we looked at the point 24.99, we would see that the pH would rise to 4.70. Okay. At the equivalence point, okay, with the addition of only 0.01 milliliters of base, the pH jumps to 7. And we've got a solution of just NaCl. Okay, so small additions right around the equivalence point do cause rapid changes in pH. And it's really important to know always that when you have the titration or the reaction of a strong acid and strong base, at the equivalence point, the pH is going to be 7. Okay, there's no calculation necessary for that. Now, if we look at beyond the equivalence point, so when we've added one very small quantity of sodium hydroxide in excess, so I'm talking about 25.01 milliliters of base being added at this point. Okay, so my total volume is 50.01. At this point, now the sodium hydroxide is going to be our limiting reactant. Okay, and it's important that, as you can see, when we're dealing with such small differences here, you need to keep lots of significant digits in your preliminary calculations so that you can actually see the difference. So now at this point beyond the equivalence point, the sodium hydroxide is actually in excess in a concentration of 2 times 10 to the negative 5. So this being a strong base dissociates completely. So I know the hydroxide concentration is 2 times 10 to the negative 5. So I can calculate the pOH of 4.70, and the pH is therefore 9.30. Okay, so as you can see, between 24.99 and 25.01, the pH has jumped from 4.7 to 7 to 9.3. So hopefully you can appreciate now, seeing the calculations, that when you're doing a titration, that one extra drop really makes the difference, and that's what really drives the pH upwards. When you're doing a titration, it doesn't necessarily mean that you're going to have an incorrect calculation if you've added, half a drop in excess, okay? Because the amount of volume that causes the pH jump significantly is really, really small. Okay. Now, when we're titrating a weak acid by a strong base, we're going to be dealing with a variety of situations. We're going to deal with weak acid calculations, we're going to deal with buffer calculations, and we're going to deal with the addition of a strong base to a buffer. The scenario that we're looking at here is with the titration of vinegar, okay, and by sodium hydroxide. As you can see here, with a weak acid, the pH initially is a little bit higher. You're also going to see that this here is the buffer region, so there's a very small changes in pH over this range as we move towards the equivalence point. The steepness around the equivalence point, the height of it, the steepness is the same, but the length of the section where it's steep is not quite as high, okay, because of the lower initial pH here. And this is where it's going to be really important for us to use the technique of taking the midpoint of the steep section in order to determine the equivalence point pH. One of the major differences of titrating with weak solutions is that the equivalence point doesn't actually lie at 7. In this case, the equivalence point is at 8.72. And we'll see in our calculations why that makes sense. So we're going to go through a series of calculations here, looking at the pH before the titration begins, okay, during the titration, halfway to the equivalence point, and at the equivalence point. So before the titration begins, we have a solution of 25 milliliters of acetic acid. It's important to make a conscious recognition that this is a weak acid. So if I want to know the pH of a weak acid solution, I need to do a hydrolysis calculation. Okay, so we've got a 0.1 molar solution, got none of this at the beginning, plus X, plus X. This is minus X, 0.1 minus X, and it's approximately equal to 0.1. Okay, then I can use my Ka, so I've got x squared is equal over 0.1 is equal to 1.8 times 10 to the negative 5, and we get a pH here of 2.87. Okay, so initially, before anything's been added, it's simply a weak acid calculation. Next, if we want to calculate the pH during the titration, so we're before the equivalence point, we are adding strong base to a solution, so we need to write the reaction for the acid that's going to react with the base, which is the vinegar plus the hydroxide. This will produce acetate and water. Because we're adding a strong base, this is a complete reaction, and we're going to use an ICF chart to organize our data. The concentration of the sodium hydroxide that we're using is 0.1, and the volume that we have at this point is 30 milliliters because we've added 5 milliliters to our initial 25 milliliter solution. Okay, Okay, so we see that we've got a 0.0833 and 0.0167. We've got none of this initially. The water I'm not worried about. Okay, so the hydroxide is going to be our limiting reactant. And so it goes down to 0, and it helps us know what our X value is, which is 0.0167. So we can figure out what the concentration of the acetic acid and the acetate ion are in the solution once the hydroxide has been consumed. Now at this point, whenever you've completed your ICF chart, you need to look at it and decide what you have. So right now we've got a solution that contains 0.0666 mole per liter in the vinegar and 0.10167 mole per liter in the acetate. So this, you must recognize, is a buffer, and so you can use the Henderson-Hasselbalch equation to very quickly and easily calculate the pH. Okay, so the pH at this point is 4.14. Okay, now next we're going to look at halfway to equivalence point. Halfway to equivalence point is a special point in the titration. So the volume at this point is 37.5 milliliters. So this is the point when half of the vinegar has been neutralized. So we started with 25 milliliters of the acid at 0.1 mole per liter, and so that is half titrated or half neutralized when we've added 12.5 milliliters of sodium hydroxide, okay, of the same concentration. So at this point, when you look at the halfway to equivalence point, you're going to notice that this is a really special point in the titration, and it will eventually become a very quick calculation. Okay, so when we've added 37.5 milliliters, what we have is our initial concentration of the vinegar is 0.0667. We've added half that amount of base. Okay. Our base is still our limiting reactant, so it goes to 0, and it helps us to determine what our X value is. Okay, now what we see here is that we've got a buffer, so we still have some of the vinegar and the acetate ions present. This is a particularly important point of the buffer though, because at this point in the titration, the concentration of the acetate is equal to the concentration of the vinegar. And when we use the Henderson-Hasselbalch equation, we've got our point where the log portion of the Henderson-Hasselbalch equation is equal to 0, because if our base concentration and our acid concentration are equal, then we'll have log of 1, which is equal to 0. So halfway to equivalence, the pH is always equal to the pKa of the acid. So you'll be able to, if you recognize this special scenario, you'll be able to save yourself some significant time in making calculations, because you can simply report that if you're halfway to equivalence, the pH is equal to the pKa. At the equivalence point is another special calculation. This one is the most challenging of the calculations that you do. So the equivalence point is the point whereby the amount of acid is stoichiometrically equal to the amount of base. Okay, so we're dealing with a 1-to-1 ratio here, and our concentrations are the same. So this is the point where 25 milliliters of base has been added. So our total volume is 50 milliliters. And so our concentrations are 0.05 and 0.5 respectively. So in this case, there is no limiting reactant. They both go to 0. They're both consumed, but the acetate ion is still being produced. So when we looked at the equivalence point of a strong acid, strong base titration, we automatically knew that we had a pH of 7. And that was because of the nature of the salt that was produced in that reaction. This salt, coming from a weak acid, affects the pH. Okay, this is the conjugate base of the acetic acid solution. So what we need to do is now look at the hydrolysis reaction that occurs with the acetic acid. Okay, the concentration of the acetate ion is 0.05. This hydroxide. And now the other major point here is that we've got the Ka for the acetic acid, but we need to calculate the Kb using Ka is equal to, Ka times Kb is equal to Kw. So the Kb in this case is 5.56 times 10 to the negative 10. Small enough to make the assumption. So we've got that is equal to x squared over 0.05. So then you can calculate the pOH at 5.28 and the pH at 8.72. Okay, so calculating the pH at the equivalence point of a weak acid titrated by a strong base is going to be slightly basic because of the presence of the acetate ion, which is the conjugate of the vinegar. We can do a similar series of calculations with the titration of a weak base by a strong acid. Okay, so there is space here for you to walk through the calculations. Okay, it's very similar. I'm going to ask you to change this to 0.10 mole per liter. Okay, so your job is to go through each of the scenarios. So you're going to look at before the titration, during the titration, halfway to equivalence, okay, and at the equivalence point. And you can compare the values that you get to the chart. Okay, that is right here. Okay, you should be getting the same pHs that we have at the particular points. And a few features of this, you can see that we've got our buffer region here where the pH doesn't change too drastically leading up to our equivalence point. You're starting with an acid because we're starting with a base, the ammonia solution, and you're adding acid to it. So the pH is gradually changing over time. The equivalence point lies at the midpoint of the steep portion of the curve. Okay. Now if you move ahead in the notes, there's a few little points here. So first of all, we already discussed that we would not titrate a weak acid with a weak base. And there's not really a clear endpoint because of the weak base that's put into the solution by the salt of this weak acid and the weak acid that's put into the solution by the salt of this weak base. So it's a competing reaction, so it's easier to avoid this kind of complex scenario. Now when we titrate with a pH meter, we're going to be able to actually determine the Ka of a particular acid. You're going to do a lab where you determine the dissociation constant of an acid by using a half titration. Okay, because we know that the pH is equal to the pKa halfway to the equivalence point. So it makes for a very simple method to calculate the Ka. Now selecting an indicator to do a titration is a really important lab technique. And what we are looking for is we are looking for a solution that's going to change color as close to the equivalence point as possible. Okay. Now indicators themselves are actually weak acids, and so the presence of H plus in the solution is actually shifting a small equilibrium to change the color of the particular indicator. The color change, okay, occurs when at the breaking point between when the concentration of one color is actually equal to the concentration of the other color. Okay, so it's a point where the concentration of the acidic form of the indicator is equal to the basic form of the indicator. This point actually occurs at the pKa of the particular indicator. So when we're looking for a indicator, we want to look for an indicator that will have a pKa close to the pH of our equivalence point. So if we look at these indicators here, okay, phenolphthalein, the indicator that you use most commonly, has a pKa of 9.3. So this is ideal for the titration of a weak acid by a strong base because the pH at equivalence is close to 9.3. The other reason that phenolphthalein is such a good indicator is because it has such a drastic color change. Okay, so those two features we're looking for. Okay, but a classic AP question is to identify which indicator is appropriate for a particular acid-base titration by using a set of pKa values. Okay, so if you have something that the equivalence point is around 4, okay, bromophenol blue might be an appropriate indicator for that titration.